Welcome everyone and thank you for joining us for our expert sessions. These are short webinars take place every 2 weeks and last no more than 30 minutes, bringing you valuable insights from the industry experts. Today's sessions will be presented by Sunny Solanki, who's Senior Technical Manager at I-Gard. Sunny is an electrical engineer with a Bachelor in Engineering by McMaster University, achieved in 2015. With 8 years of experience in protection system and relay. Through his career, he has educated consultants and end users of the benefits of integrating electrical protection products into their designs to enhance personnel and equipment safety. He specializes in providing commercial and technical support for various projects and applications, including high-resistance grounded systems, low-resistance grounded systems, hybrid HRG systems, ground fault, and arc flash protection systems, resistor-based solutions, and personal protection products. We are excited to have him here today, and we appreciate your participation. Let's get started.
So hello everyone, my name's Sunny, as Andrea mentioned, and today we're going to be talking about arc flash risk and magnitude reduction with high resistance grounding and the optional module we provide. So let's start off with what is an arc flash. So the National Fire Protection Association, or NFPA, defines arc flash hazard as a dangerous condition associated with the release of energy caused by an electrical arc. The arc flash occurs when there's a breakdown in the insulation between two conductive objects. This breakdown can be caused by a number of factors, including human error, equipment failure, or environmental factors such as moisture or dust that result in phase-to-ground and/or phase-to-phase electrical faults. So the questions that we have to ask are, what is the probability of an arc flash occurrence? And if it does occur, what would be the magnitude of its severity? So here we can look at NFPA 70E, which is standard for electrical safety in the workplace. And in Annex O.2.2, it says that design option decisions should facilitate the ability to eliminate hazards or reduce risk by doing the following: reducing the likelihood of exposure, reducing the magnitude or severity of exposure, enabling achievement of an electrically safe work condition. Further to this, in Annex O.2.3, they list out 9 different incident energy reduction methods that can be utilized to reduce the likelihood and also the magnitude. So reducing the likelihood of exposure, what is the probability of an arc flash occurrence? So going back to NFPA 70E, to reduce the likelihood of exposure, high resistance grounding is one of the only incident energy reduction methods that is reducing the likelihood of exposure from the 9 that are listed. High resistance grounding is when we place an impedance in the ground return path and will typically limit the fault current to 10 amps or below at 5 kV nominal or below, leaving insufficient fault energy and thereby helping reduce the arc flash hazard level. High resistance grounding will not affect arc flash energy for line-to-line or line-to-line-to-line arcs, because usually we're grounding with the resistor at the source, and if there's a line-to-line or line-to-line-to-line arc, the two faulted points would be circulating current between each other, and the high resistance grounding would be bypassed. But high resistance grounding does a good job for 95% of the cases being phase to ground type, where it can limit that fault current. And because we're limiting that fault current, we're basically reducing the arc flash from gaining more and more current and energy by clamping that current to a known value of 10 amps or below. So we could see that high resistance grounding does offer its advantages over ungrounded and solidly grounded systems. We can still achieve process continuity under the ground fault condition with high resistance grounding, similar to ungrounded systems. We can also control the transient overvoltages better than an ungrounded system by sizing the resistor in accordance to the capacitive charging current. We also have the ability to locate ground faults, and prevent damage in shorted transformer and rotating machine windings. We also reduce the likelihood of arc flash, but what we're missing is what can we do to reduce the magnitude of the arc flash? So for the magnitude, what would be the magnitude of its severity if an arc flash were to occur? So going back to NFPA 7D, we realized that we needed to do something to accompany high resistance grounding in order to reduce the magnitude for line-to-line and line-to-line-to-line arcs. In this case, we have selected an arc flash relay. So an arc flash relay typically uses light sensors to detect the light produced by an arc flash event. Once a certain level of light is detected, the relay will issue a trip signal to an upstream overcurrent device, and that will reduce the arc magnitude because there's no energy available for the arc to go on its exponential path to higher energy levels. So this arc flash relay is looking at what is the arc flash impact. So the power of an electrical arc, which shows how much damage it can do, depends mainly on two things: how long the arc lasts and how strong the electric current is. The longer the arc and the stronger the current, the more destructive the arc can be. So you can see here on the graph on the right that as time passes, this energy level begins to increase to significant levels. And we want to make sure that we can reduce that by having a trip time that is on the lower end of this curve. If we look at IEEE 1584, they give out intermediate incident energy equations with respect to what voltage you are specifying for. In each of these equations, time is directly correlated to energy. So if we reduce the time that the energy is in the system, we can reduce the magnitude. Here are some examples as to if we are able to trip within 3,500 or 500 milliseconds and the associated damages and the incident energy that was calculated. So for 35 milliseconds, there's no significant damage to person or switchgear, which can often be returned to use after checking the insulation resistances. And we're dealing with 2.9 cal per cm squared. When it comes to 100 millisecond, there could be small damage, requires cleaning and possibly some minor repair is likely. And we're at 8.31 cal per centimeter squared. When it comes to 500 milliseconds, there could be large damage both for person and the switchgear, which must be partly replaced. The arc burning time is the sum of the time to detect the arc and the time to open the correct breaker. So on the 500 millisecond side, we're dealing with 41.58 cal per cm squared. Based on 50K, these are based on 50K maximum voltage fault current on a 480 volt solidly grounded system at 18 inches of working distance. Now, an arc is accompanied by radiation in the form of light, sound, and heat. Detecting these can help identify the presence of an arc. Analyzing visible light, sound waves, and temperature changes can reveal if there's an arc, including pressure. In this graph, the energy developed by the internal arc generates heat and pressure. So we can see that for the short circuit current, we have that as part of the A portion. The arc voltage will be the B portion, and the C portion is the internal pressure, which is indicated here. Now, to offer something better than the standard HRG offering, we've designed our DSP system to provide additional caveats to the standard HRG solution. So from left to right, we have our communication module, which sends all the information to our touchscreen display, a power supply that manages the power to all the modules in the system, as well as the pulsing feature of the resistor. We also have our DSM, which is detecting the phase shift in voltage on the phases for when a ground fault occurs. Our resistor monitoring module, which monitors the resistor for both open circuit and short circuit. And we also have feeder modules, which are basically connected to CTs at each of the feeder with the option to trip at the feeder breaker trip. In addition to that, we've also included our arc detection module, which uses arc flash sensors throughout the gear to pick up when an arc flash hazard is present by detecting the spectrum of light emitted by an arc flash incident. In this case, this arc detection module will accompany this HRG design to reduce the magnitude. So this is the module here, and it's usually placed towards the end of the line for these modules. And the aim is to diminish the incident energy, thereby reducing the magnitude of the arc flash. So arc detection modules proactively identify, notify of electrical arcs in systems by monitoring light and/or air pressure, providing an added layer of security for your operations. The DSP ADM is designed to be used with sensors like point light sensors, modified point sensors with fiber optic tail, as well as pressure arc sensors. So in this case, we would have the DSP system integrated into the switchgear. When an arc is detected and the fiber optic sensor is picking up that arc, then we send a command to the breaker to effectively trip the system. Now, the timing for this is quite quick because the light sensors pick up within 1 microsecond and then send a command out to the breaker as fast as possible. From there, the breaker selection, usually we were dealing with like 5-cycle breakers. So that's approximately maybe 100 milliseconds on that front. And we would be tripping that breaker as fast as we can with our signal. So we could see that smart high resistance grounding is advancing on the standard HRG offering by providing this additional level of protection for reducing the magnitude in terms of phase-to-phase and phase-to-phase-to-phase failures. If you have any questions, feel free to ask and I'll be going through them right now. Hi, can we get a recording of these webinars and previous webinars? So Ravinder will be sending that out. They will be available on our YouTube channel. Also an email with the recording and the certificate and the PowerPoint will be shared. Which standard does the module fulfill? Off the top of my head, I'm not entirely sure, but I can definitely get an answer to that and get back to you, Farzad, on that point. Are there any additional questions that would like to be asked at this time? Is there a protocol regarding the method of installation of the light sensors? Well, I think it depends on whether you have like a metal clad switchgear and what points where we would have blind spots in the actual arrangement within the switchgear cabinet. Sometimes we have utilized probably 3 sensors per section. So that might be an initial starting point for this design. Are there light and pressure sensors adjustable? They are not adjustable. So for the pressure sensor, because it's mechanical, it's going to act a little bit slower at around 10 milliseconds versus the light sensor, which is strictly electrical and light based with fiber optics, which is our fastest solution. Now, the pressure sensor's sensitivity is between 0.2 to 0.5 BAR. And with respect to the next question in terms of custom procedure based upon the application, you're correct, Andy. It will have to be sensitive to the application, and we would probably need to interface with the switchgear manufacturer and give them advice on where to place these sensors. Sorry, let me go through this. Will the system have nuisance tripping if external light shines on the sensor? The answer is no, because we're looking for a particular spectrum of light emitted by the arc flash condition, and that is a very particular spectrum such that we avoid nuisance tripping. Can you discuss the DSP's ability to monitor each feeder and trip the lowest priority feeder upon second phase to ground fault? We can, for sure, Charles. So the DSP system, upon first fault, you don't have to trip because the fault is being limited to 5 or 10 amps on as a standard. But if there's another fault on another feeder on another phase, we have a phase to ground to phase failure where the current circulating between these 2 points is going to get extremely high. In this case, if you didn't have the DSP system, your instantaneous function of your breaker would trip out both of the faulted feeders due to the high level of current detected by the instantaneous function. What our DSP system is designed to do, though, is to have a lower pickup of 100 amps, such that before the instantaneous can even react, we selectively trip the lower priority of the 2 feeders that are faulted so that we can revert back to our first fault condition. Will flash from a camera trigger the arc flash module to trip a breaker? No, it will not, because we're looking for a particular spectrum of light. Does the unit have self-diagnostics provisions? Usually when we have this unit set up and commissioned properly, we don't need to do much self-diagnostics, but I will have to check and see if we also do a test feature for the Arc Flash module to confirm that for you, Manuel. Are false trips a problem? No, they are not, because we're avoiding nuisance tripping when it comes to detecting the particular spectrum of light and not just any light going to these fiber optic sensors. Are there light only or light and current sensing? We do have an option for light and current sensing, and that is our Architect relay. At the moment, this module is only focusing on light and pressure at the moment. What about medium voltage systems without CTs? For example, fuse load break switches. For medium voltage systems, we would recommend using the Architect relay so that you can have CTs and light detection. Typically, the DSP system is reserved for systems that are strictly 5 kV or below. Will we get any PDH credit for this webinar? I believe that Andrea has answered that in the first response, and we will be issuing out those PDH certificates. What kind of external power is needed to be able to maintain functionality during a fault? Well, we have power to the relay, and when the fault occurs, we will be tripping the upstream breaker. Depending on how the relay is powered, the breaking open of that main breaker may cause the relay to shut down if you have CPTs connected on the load side of the main breaker. But if the CPT is connected on the line side of the breaker, we should be able to still be able to pick up the fault scenario. Is there a chance of conflict with PNC systems? It's possible, but I think you would have to work on the coordination of the settings for your protection and control system with respect to the other relays that are also offering protection and control, so that we have a method of organizing and coordinating those protection and controls. Are these point sensors only, or can you also connect fiber loop sensors? I believe that these are point sensors only, but we may also be able to do fiber loop sensors. I think I'll have to seek clarification on that. In most of the cases that I've been involved in, we've only used point sensors, but I can ask about the fiber loop sensors and get back to you, data tray. So thank you for coming to this presentation. We really appreciate your support and consideration in that matter. As mentioned by Andrea, the details of the recording and the certificate and the PowerPoint will be shared to each attendee of this webinar. And I hope you learned something and enjoyed these expert sessions that we're doing. Our next one is on March 18th, I believe.
Yes,
So stay
correct.
tuned for that one. Thanks again, guys.